Hi and welcome to another lesson about basic assembly. This time we are going to talk about basic conditional branching. Objectives of this lesson. You will learn about the jump 0 and jump not 0 conditional jump instructions and see examples of their usage. We will also briefly mention some other basic conditional jumps. However, we are not going to deal with them a lot at this point. We are only going to mention them. Jumping according to flags. The JMP or jump instruction changes the value of EIP unconditionally. That means that if you put this JMP instruction somewhere, the jump instruction, it is just going to change the value of EIP every time that the flow of the program passes at this instruction. We don't actually have any control of whether the jump is going to happen or not. We would like to be able to jump only on certain conditions. There is a family of instructions of the form JCC where the CC here is replaced by some condition. So the instruction doesn't actually look like JCC. It is usually J and then some two letters, or maybe a bit more, that represent the condition. In those instructions, the jump is taken only if the condition is fulfilled. The condition is usually based on the values inside the flags register. Let's see an example. The jump 0 instruction. It looks like this. Jump 0 and some label. This instruction takes the jump only if the 0 flag is set. It means that it takes the jump only if the result of the last calculation was 0. Otherwise, the flow continues as usual. Let's see two examples. In the left example, we can see that we have some instructions and also the jump 0 instruction among them. Let's try to understand the example. First we move the value 1 inside AX. I remind you that AX is of size 16 bits. Then we decrease AX. Now we have the jump 0 instruction to my label. We can see that my label exists in this code and it is here. This jump instruction, the conditional jump, jump 0, is going to take the branch only if the result of the last calculation was 0. In this case, it is indeed going to be 0 because we moved 1 inside AX and then we decreased it by 1. So the last result is going to be 0, and so the 0 flag is going to be 1 at this point after this decrease instruction. Therefore, the jump is going to be taken, and we are going to jump from this instruction to the add AX2 instruction, which means that we are going to skip the add AX5 instruction. Let's try to calculate what is going to happen. AX is first of value 1, then it is going to be of value 0 here after this instruction, which is going to cause this instruction, the conditional jump, to jump to my label, and finally we add 2 to the value of AX, which means that the final value of AX is going to be 2, as written here. Let's look at the right example. Again we move 1 inside AX, and then instead of decreasing like in the left example, we are going to increase AX by 1. Then we have the jump 0 instruction. This time, after the increase instruction, the value of the 0 flag is going to be 0 because the last instruction didn't produce a result of 0. The result produced by the increase instruction was 2, which is non-zero. Therefore, the jump 0 instruction is not going to take the jump, which means that the flow continues as usual, and we move on to this instruction, the add AX5 instruction. Eventually, after invoking this instruction, the add AX5 instruction, we are going to move on to this instruction, add AX2. So let's try to calculate the final value of AX in this example. AX begins with the value 1. We increase it by 1 and we get 2. The jump 0, or the conditional jump here, will not be taken. So we move on to this instruction and we have 2 plus 5, which is 7. Then we move on to this instruction and we have 7 plus 2, which is 9. Eventually, we get AX equals 9. In the left example, the jump was taken, so the flow of the program was changed. In the right example, the jump was not taken. I want to mention the opposite instruction, JNZ, or jump not 0. This instruction does the opposite of the jump 0 instruction. It jumps only if the 0 flag is cleared. The jump 0 instruction jumps only if the 0 flag is set. So actually, jump not 0 is the opposite of jump 0. Let's look at another example, this time maybe a bit more useful than the previous one. This one is going to be about a simple loop. Let's take a look at the code that we have here. First we move 0 inside EAX and then 3 inside ECX. Now we can see that we have some kind of loop. We have this jump instruction that always jumps to some previous location called again. And this conditional jump, which is called outside, which has the ability to take us outside of this loop. We can see that outside is here. So actually, if we didn't have the jump 0 instruction, this loop would just go on forever. We have already seen this kind of infinite loop. But the jump 0 instruction is some kind of a termination condition. It could let us out of this loop. Let's take a look at what happens when we run this code. We are going to follow these three values: the value of EAX, the value of ECX, and the 0 flag. At the same time, we are going to follow, maybe virtually, the value of EIP, which is the current instruction. I remind you that EIP is a register that always points to the next instruction to be executed. EIP means instruction pointer or extended instruction pointer. So we begin with this instruction, move EAX 0. I want to tell you before we begin that every time that a value changes in the last instruction, it is going to be marked with purple. So let's begin. Here we can see that the value of EAX has changed to 0. Now the value of ECX has changed to 3. Next we are going to add EAX and ECX and store the value inside EAX. The result is 3 inside EAX. Next we are going to decrease ECX, which gives us 2 inside ECX. Now we check for 0, which we don't have. We can see that the 0 flag is of value 0. Therefore we are not going to jump outside. The flow is going to continue as usual. The next instruction is jump. And this jump is unconditional jump. It is always taken. So we move back to the again label. And again, we add EAX and ECX and store the result inside EAX. We get 5. Again, we decrease ECX. We don't have any 0 results, therefore the jump 0 is not going to be taken. and we jump to the label again. Again, we do the same instruction of adding ECX to EAX. We decrease ECX, and this time we have a different result. ECX is now 0, therefore the 0 flag is set. It is set to 1. And this time, jump 0 is going to be taken. And we are going to be taken outside. I want to take a look again at this example. I want you to follow the value of ECX. Initially, it is of value 3, and we can see that the only modification to ECX in this loop is this, decrease ECX, which means that ECX is some kind of a backward counter. ECX is actually the amount of iterations we are going to do in this loop. In every iteration, ECX is decreased by 1. And the jump 0 instruction waits for ECX to become 0. Only when ECX is 0, we exit this loop. So let's take a look again. This time, pay attention to the value of ECX. This is the last time that we can decrease ECX before it is 0. It is decreased. The value of ECX is now 0. And the 0 flag is set to 1. Now we can exit the loop. We can actually see, you probably have seen it yourself already, that this simple loop calculates the value of 1 plus 2 plus 3, which equals 6. The result is inside EAX. So EAX is actually the sum of all the numbers that are added. Think for a moment, how could you change the program to make it calculate 1 plus 2 plus 3 until 100? You probably guessed it right. It would be enough to change this number 3 into a decimal value of 100. Using jump node 0. We could use jump node 0 instead of jump 0 in this specific example to get simpler code. This is the original code that we have just looked at in the previous example. The loop that sums the numbers 1, 2, and 3. In the ending of this loop, we had this termination condition, jump 0 outside, which can get us outside of the loop, and jump again, which always takes the jump and iterates to the next iteration of the loop. Instead, we could replace those two instructions, the jump 0 and jump, with one instruction of jump node 0. In this example, we only jump to the again label if ECX is not yet 0. So we keep the loop as long as ECX is not 0, and at the moment when decrease ECX results in the value of 0, we don't take the jump, and the flow just continues as usual, and we exit the loop. This is a bit of a cleaner formulation for the loop. We can see it in the right example. We actually get the same behavior, maybe even similar speed, similar running speed. However, the code in the right example is a bit simpler. So usually I prefer this kind of code, like the one in the right example. Some other basic conditional jumps. We have already discussed the jump 0 and the jump not 0 conditional jumps. I want to show you some other possibilities. We have the jump sign and jump not sign. This means, at least for the jump sign, jump if the sign flag is set. Jump not sign jumps if the sign flag is cleared. Similarly, we have those conditional jumps of jump carry and jump not carry, which, as expected, jump only if the carry flag is set or cleared. And those instructions, jump overflow and jump not overflow, which jump if the overflow flag is set or cleared. We are going to use those flags and maybe even those conditional jumps a bit later, so we are not going to discuss them in a very detailed manner at this point. Don't worry, you are going to have enough opportunities to deal with those flags, the sign, carry, and overflow. Summary. The conditional jump instruction, JCC, which is actually a family of instructions, allows us to take branch decisions based on the flags register. We also created a loop, for example, that sums the numbers 1 plus 2 plus 3. And we also discussed how to generalize it to sum the numbers 1, 2, 3 until 100, for example. The conditional jump instructions are some kind of an indirect way of reading the flags register. We said that we cannot read the flags register directly. However, we could use the conditional jump instructions to have some kind of side effects which we can use to read the flags register. We can extract information from the flags register using the conditional jump instructions. Some exercises. This time we know enough things to be able to actually write some code and read some code. The exercises contain some code reading and some code writing. Make sure to do the code reading first, so you can get the feeling of how using conditional jump instructions look like. Only then move on to the code writing. It is very important that you do these exercises to make sure that you understand the material and to be able to do the next lecture and also the next exercises which build on these exercises. So have fun and see you next time.